evening, everyone, and welcome to today's session. As this is an extra class, so we'll just try to visit the same concepts which we have covered throughout the 4 week of this particular course. I'm not sure whether your exam has been done or not for this particular subject, that is bioelectrochemistry. But if it's not yet done, this revision will help you out in just summarizing the things which we have learned in first, second, third, and fourth week of this course. As I have told you since the beginning of this course, that this is a very uh, introductory course for the bioelectrochemistry. A lot of things which you guys want to know or go deeper into it, for that this particular course will make the foundation, right? So we'll get to all those nitty gritties of the things, maybe not this time, as this is just the summary session which I'm taking, so that it can help you in summarizing the things which we have learned. Because gradually, as we go deeper into the subject, sometimes we forget what we have learned actually, or from where we have began this course, right? So with that respect, I have not changed the material much. I have just culminated what we have learned in our previous classes. As and I'm not gonna share any videos or those things. They're already present in the lecture slides, so we can have uh, like the links you can take from the slides itself. Okay, with this, I guess I'll wait 5 more minutes so that people can join in, and then we can begin our lecture. Okay. Yeah, I guess we can start with our lecture. So the first thing first, in the first week itself, we discussed about what is bioelectrochemistry, right? So bioelectrochemistry is an interdisciplinary field that combines principles of biology and electrochemistry to study the interactions between electrical processes and biological systems. It focuses on understanding how biological molecules, cells, and tissues interact with electrical signals or undergo electrochemical reactions. This field has significant applications in medicine, biotechnology, and environmental science. Key areas of bioelectrochemistry includes electron transfer in biological systems, that is studies it basically studies the redox reactions in enzymes, proteins, cytochromes, and other biomolecules. Explores the role of electron transfer in processes like photosynthesis, respiration, and metabolism. Biosensors, it basically deals in develops devices that use biological molecules, example enzymes, antibodies, or DNA, to detect specific substances such as glucose in diabetes monitoring. Third, electrochemical techniques. It uses Techniques like voltammetry, amperometry, and impedance spectroscopy to study biological systems. Fourth, bioelectronics. It involves interfacing electronic devices with biological systems such as neural implants or pacemakers. Electrochemical energy conversion. It examines how biological systems can produce or store energy, like in biofuel cells. Electroporation. It studies how electric fields can be used to increase cell membrane permeability, aiding in drug delivery or DNA transfection. Seventh, bioelectrochemical systems for environmental applications includes microbial fuel cells and bioelectrochemical reactors for wastewater treatment and energy generation. Few of the applications of biochemistry are enlisted here, and they are not limited to this only. Okay, there are some of the applications of bioelectrochemistry. First, medical diagnostics. Glucose sensors, electrochemical DNA detection, therapeutics, development of neural prosthetics, cardiac pacemakers, and drug delivery systems. Energy production, biofuel cells for renewable energy. Environmental science, monitoring and treating pollutants through biochemical systems. This field bridges fundamental research in biology and practical applications in engineering and medicine, making it highly impactful and versatile. The whole of the bioelectrochemistry is based upon the chemical aspect of the living system. Okay, but before that, if we want to understand bioelectrochemistry and the chemistry behind this, we need to understand what sort of reactions or chemical reactions we are talking about. So majorly the whole field of bioelectrochemistry, or cells majorly, or the batteries majorly, they take the use of spontaneous reactions, and these sort of reactions are generally redox in nature. So what is a redox reaction? A redox reaction, it is short for reduction oxidation reaction, is a chemical reaction in which electrons are transferred between two substances, leading to changes in their oxidation states. It involves two simultaneous processes: oxidation and reduction. Oxidation means the loss of electrons by a substance, increasing its oxidation state. Okay, so oxidation means loss of electrons. Reduction, that is the gain of electrons by a substance, decreasing its oxidation state. Okay, so loss of electrons means oxidation, and gain of electrons means reduction. What are the key features of redox reactions? First, electron transfer. Electrons are transferred from the species undergoing oxidation to the species undergoing reduction. Why? Because they are always coupled, right? That is why they are called redox, because they'll have an oxidation component and an reduction component. So the oxidation component, it will lose the electron, and the reduction component, it will gain the electron. Similarly, electrons will be transferred from oxidation side to the reduction side. Okay, coupled processes. Oxidation and reduction occur together. If one species is oxidized, another must be reduced. Change in oxidation state. The oxidation state of the species changes as a result of the reaction. Why? Because one species is losing the electron, that is oxidation, and another species is receiving that electron, that is reduction. Okay, so the key features of redox reactions include electron transfer, coupled process, and it is associated with the change in the oxidation state of the substances. Some of the example of redox reaction can be seen here. So you can see Zn plus Cu2 positive gives Zn2 plus. It's a simple reaction in which Zn loses 2 electron, and that is why it converts into Zn2 plus, which means the oxidation is taking place. And Cu2 positive, it gains these 2 electrons and converts into Cu, that is, it is reduced. Okay, combustion. So in combustion what happens, it is the burning, right? So CH4 plus 2H2O2 gives CO2 plus 2H2O, right? So C is oxidized because in CH4 the oxidation state of C is plus 4, right? It increases to plus 4, and in an O2 is reduced, as in O2 the oxidation state is decreased from -2 in H2O. Rusting of iron is also a type of redox reaction. Okay. Applications of redox reactions. First, energy production. Redox reactions power batteries and fuel cells. Metabolism. Biological systems use redox reactions for energy in cellular respiration. We'll discuss it later. Corrosion and protection. Understanding redox helps prevent rust and design protective coating. Environmental chemistry. Redox processes are involved in water purification and pollutant degradation. We'll see a little bit about what is a redox reaction and how we can use it for our benefit and what are some of the uses. Okay. Let me.
Hey developers, join us for the biggest.
Just give me 1 minute.
In today's video, we're going to take a look at redox reactions, which are reactions in which oxidation and reduction both take place at the same time. And to do this, we'll cover displacement reactions, ionic equations, and half equations. We saw in a previous video that one meaning of oxidation is the gaining of oxygen, and that reduction is the loss of oxygen. For example, if aluminium reacts with oxygen to form aluminium oxide, we can say it's been oxidized. Whereas if we take away that oxygen, then it's been reduced. The terms oxidation and reduction can also refer to the loss and gain of electrons though. And instead of just remembering which is which, most people use the mnemonic OIL-RIG, which stands for oxidation is loss, reduction is gain, and this refers to electrons. So if we had a magnesium atom, and it loses 2 electrons to become a 2+ ion, then it's been oxidized. And if it gained those 2 electrons back, then it would have been reduced. Most of the time though, these oxidation and reduction reactions don't happen by themselves. Instead, they both take place at the same time. Because if one substance loses electrons, then another substance has to gain them. And because both happen together, we call them redox reactions, which just means reduction-oxidation reactions. For example, if we react some magnesium with a dilute acid, which we can represent as H+, because that's the important part of an acid, then the magnesium atoms will lose 2 electrons and be oxidized, forming magnesium 2+ ions. Meanwhile, the hydrogen ions will gain those electrons and so be reduced to neutral hydrogen atoms in the form of hydrogen gas. Another place we see redox reactions is in displacement reactions, which involve a more reactive metal displacing a less reactive one. For example, if we look at our reactivity series, we can see that calcium is more reactive than iron. So if we added some calcium to a solution of iron sulfate, then the calcium would displace the iron to form calcium sulfate, while the iron would precipitate out as a solid. For reactions like this, it's sometimes useful to write them as ionic equations, in which we only show the particles that actually take place in the reaction and change in some way. For example, if we showed everything here as ions, we can see that these sulfate ions stay as SO4 2- ions. They don't actually change or take place in the reaction by exchanging electrons. Because of this, we call them spectator ions and get rid of them from our equation. And what we have left is the ionic equation. We can actually break this down even further though, by writing individual half equations which show the gain and loss of electrons for each of the elements involved. To do this, we first copy the ionic equation, but only for one particular element. So for calcium, we would write that a neutral calcium atom goes to form a calcium 2+ ion. Next, we need to add our electrons to make the charges balance. As the calcium atom loses 2 electrons, we can think of the calcium ion as one product, and the 2 electrons as another product. So we put plus 2 electrons on the right-hand side. Then for iron, we show the iron 2+ ion going to form an iron atom, and then again think about our electrons. This time the iron ion gains 2 electrons, so we place the 2 electrons on the left, because they have to combine with the iron ion. Whenever you do these half equations, just check that the overall charge on each side balances. For example, in our iron half equation, we can see that on the left we have a 2+ charge and 2 1- charges, which add together to make 0. And on the right, everything is neutral, so also 0. If you ever find that the overall charges on each side aren't the same, then you've probably put your electrons on the wrong side. Anyway, that's all for this video. So if you enjoyed it, then please.
So that was the basic of redox reaction. Now coming to galvanic cell, then if you remember, we covered a wide portion of galvanic cell in the lectures itself. So what is a galvanic cell? A galvanic cell, also called a voltaic cell, is an electrochemical cell that generates electrical energy through a spontaneous redox reaction. It consists of 2 half cells connected by a salt bridge or porous membrane and an external circuit that allows electrons to flow. Key components of a galvanic cell: 2 electrodes. First, anode, the electrode where oxidation occurs. You remember what was oxidation? So oxidation was loss of electrons. Okay, and cathode, that is the electrode where reduction occurs, that is gain of electrons. So anode, at anode oxidation will occur, that is loss of electron. So whatever the material at anode will be, it will be losing the electrons. Okay, and cathode, here the reduction will be taking place, meaning the electrons which are given away by the anode side will be received at the cathode, and there will be electron transfer. You remember the key feature of redox reaction is the transfer of electrons. Okay, so the electrons will transfer from oxidation side to the reduction side. Here the oxidation side, the oxidation will occur at anode, hence the electrons will flow from anode to cathode, and the current will flow from cathode to anode. Okay, in the spontaneous reaction. Second, electrolyte solutions. Each half cell contains an electrolyte that provides ions for the redox reactions. Okay. Third, salt bridge or porous barrier. It maintains electrical neutrality by allowing ion exchange between the 2 half cells, preventing charge buildup. External circuit connects the electrodes, allowing electrons to flow from the anode to the cathode. So all these things we have already learned and discussed. Okay, so in a galvanic cell, which is the first spontaneous cell, here the components of galvanic cell includes the electrodes. At one electrode where the oxidation will happen, the electrons will be lost, that side is called anode, and another electrode where these electrons will be accepted, where the reduction will take place, that is called cathode. There will be an electrolytic solution so that each half cell have their respective ions, and then a salt bridge or a porous barrier will be there so that the neutrality of the solution and the system can be maintained. Otherwise there will be charge accumulation, due to which there will be decrease in the efficiency of the oxidation and reduction, and an external circuit so that electrons can be flown through it. So basically, how does a galvanic cell works? So as we have seen in the previous slide itself, that anode and cathode, at anode oxidation will occur, at cathode reduction will occur. Okay, so the oxidation at anode means there will be a element or a metal which will lose electron, forming cations that enter the solution. Okay, we'll see in the coming slides how. And also you guys have already learned about the galvanic cell. Reduction at the cathode. Electrons travel through the external circuit to the cathode, where they combine with cautions from the solution. Electron flow. Electrons flow from the anode, that is negative electrode, to the cathode, that is the positive electrode, through the external circuit. Ions flow via the salt bridge. Anions migrate towards the anode and cations migrate towards the cathode to maintain charge balance. Okay, so this is one example of a galvanic cell in which Zn and Cu are there. Okay, then the key characteristics of galvanic cells are electromotive force. So the voltage produced by the cell determined by the difference in the reduction potentials of the two half cells. Spontaneous reaction. The cell operates spontaneously because the overall reaction has a negative Gibbs free energy. Applications of galvanic cell includes, galvanic cells are the best and the basis for batteries such as alkaline battery, lead acid batteries and lithium ion batteries. Now we'll see little bit brief about the galvanic cell. Okay, again I am saying I am not introducing any new material. All these things are already
The fact is, we've come.
you have already learned and discussed. We have already done that. Okay,
Or voltaic cell is the most easy and fundamental cell to understand. Let's take a look at this animation to see how this cell produces a voltage and current flow. It all starts with two materials, zinc atom and copper ion. The zinc atom always wants to lose 2 electrons. Only when it loses 2 electrons does the zinc atom become stable. However, in order to achieve stability, the copper ion wants to accept 2 electrons. Therefore, if we connect them together through a conducting cable, there will be 2 electrons flowing through them. If we can produce more such zinc atoms and copper ions in a sustainable way, then we will be able to achieve a continuous flow of current through the connecting cable. Let's see how we can achieve this. To produce copper ions and zinc atoms sustainably, let's use a copper sulfate solution, which is composed of numerous copper ions and a zinc metal bar, which, as the name implies, contains a lot of zinc atoms. The copper ions in the solution are starving for electrons. If we connect the solution and the metal bar together, then the zinc atoms in the bar will want to donate their electrons. But after donating, the zinc is transformed into ions, and ions cannot stay in a metal. So we'll have to introduce another aqueous solution around the zinc metal bar to accommodate these new zinc ions. Now the electrons flow through the circuit, generating electricity, and the copper ions receive them. Once received, the copper ions become atoms. To accommodate these new atoms, we need a copper metal bar. This unique arrangement will produce a voltage and electron flow. However, there is an issue. You might have noticed that in the course of this process, positive charges are accumulated on the left side and negative charges are accumulated on the right side. As these charges build up, they block the journey of electrons. Here you can clearly see how the built-up charges impede electron flow. Therefore, proper measures must be undertaken to ensure that the electron flow is continuous. A simple solution for this is a salt bridge. The salt bridge is an aqueous solution with a lot of Na+ and Ci- ions inside it. This bridge is blocked at both ends with cotton material. However, this cotton material is capable of conducting the Na+ and Ci- ions. If the charge outside of the salt bridge is positive, then negative ions will get out, and vice versa. What exactly happens when the salt bridge is introduced in between the chambers? The excess positive charges on the left side will obviously attract the negative ions inside the salt bridge. These ions will leak out and neutralize that region. The exact opposite process will happen on the right side, and there also the accumulated charges will get neutralized. In short, the introduction of the salt bridge made the voltage and electricity production sustainable. The cell we have just created is known as a galvanic or voltaic cell. You can observe that over time, the zinc metal bar erodes as it loses zinc ions, becoming thinner and thinner. The exact opposite happens on the copper plate side, which becomes thicker. The galvanic cell will continue its operation until the zinc is completely depleted or the ions in the salt bridge have been completely exhausted. We hope you have enjoyed this video and that it gave you a
Right? So this is the basis of galvanic cell. I request everyone to please mute your mic. So over here we are just discussing whatever we have already learned in the previous classes. I'm not introducing anything new here. I'm just explaining the same slides. So can you please mute yourself? Hello?
Hello.
Can you hear me? Yeah. Can you please mute yourself? There is little bit of disturbance from your side.
Okay.
Yeah. So as we have seen that galvanic cell is the basis of batteries which we are working with nowadays, right? And it is being improved on daily basis. The basis of galvanic cell is the spontaneous reaction. And what is the spontaneous reaction? It is a redox reaction. This is what we have learned till now. So redox reaction, as it has two components, reduction and oxidation. So oxidation means loss of electron, reduction means gain of electron. With respect to the galvanic cell, the oxidation will take place at anode and reduction will take place at cathode. Hence, electrons will move from anode to cathode and current will flow from cathode to anode. Okay. So in a battery, the electrodes, that is the anode and the cathode, are responsible for the flow of electrons that generate electrical energy. However, to function properly, the electrodes must be physically separated to prevent direct contact, which could lead to a short circuit. So role of the barrier material, which we have seen here, we are keeping them in separate jars or separate solutions or vice versa, right? It can be anything. Either you are physically separating them or you are keeping them in a different solution. So the role of the barrier materials include to prevent the anode and cathode from touching, a separator is placed between them. This separator is typically made of a porous material, allowing the passage of ions while blocking the direct flow of electrons. The key functions of separator or the barrier material are: first, to prevent a short circuit. Okay, if the electrodes come into direct contact, electrons would flow freely between them without passing through the external circuit. This would lead to an uncontrolled reaction, excessive heat generation, and possibly battery failure. Second, allow ion flow. The separator is designed to be electrically insulating but ionically conductive. This is important, right? Otherwise, if it is not electrically insulating, again, keeping a separator, the job will be not done at the end of the day. Why we are keeping a separator? So that there should be no short circuit and there should be no free flow of the electrons, right? So the material whatever we are selecting to be as a separator, it should be electrically insulating, but it should allow some of the ions to be flow through it, meaning it allows the movement of ions through the electrolyte while preventing electrons from moving directly between the electrodes. And this actually helped us in reducing the size of the batteries. Okay, maintain battery efficiency by direct electron flow by directing by directing electron flow through an external circuit. The separator ensures the battery delivers power efficiently to an external load. Last but not the least, enhance safety. Many battery failures occur due to separator damage, leading to short circuits and overheating. High quality separators improve battery safety and longevity. Okay, nothing to discuss much about this. It's a very straightforward thing that why we need to keep the two electrodes separately, because if we are not keeping the two electrodes separately, due to the spontaneous nature of the reaction, that is the redox reaction in which they are involved, they'll freely flow the electrons between them, and this process will be so spontaneous and so exergonic that it will release energy, right? And the system in which we are making the observation, it will overheat and at the end it will lead to the short circuit. So to make sure that this doesn't happen, we have a separator material or a barrier material between the two electrodes. Now, a battery is there, we use it daily, we also recharge it, right? So why is recharging non-spontaneous and it's an energy dependent process? First of all, what is a non-spontaneous process? In a battery's discharge phase, the chemical reactions occur spontaneously, as we have seen till now. Okay, so anode, the oxidation will occur, cathode, the reduction will occur, and this is a spontaneous reaction. So in a battery's discharge phase, the chemical reactions occur spontaneously, generating electrical energy. This means the Gibbs free energy change, that is delta G, or the free energy change, is negative, indicating that this process is a spontaneous process. However, during recharging, we are reversing these reactions, which is a non-spontaneous process. That is, delta G will be positive, or the free energy change will be positive. To make it happen, we need to supply energy from an external source, because it is not happening on its own. We need to supply energy from the outside. Second, external energy input. To reverse the discharge reactions, and here what do we mean by reversing the discharge reactions? As we have seen in the galvanic cell, the electrons which are flowing from anode to cathode, so there is accumulation of some charge in anode and cathode respectively, right? So cathode is the positive terminal and anode is the positive terminal and cathode is the negative terminal, correct? So to balance this out, to reverse the distribution of charge so that the battery again can function as a spontaneous reaction, we need to reverse the discharge reactions. So an external voltage is applied which forces electrons to flow in the opposite direction. This energy input drives the oxidation reduction or the redox reaction at the electrodes, restoring the battery's original charged state. Complementary redox reactions. The oxidation reaction that took place at the anode during discharge now will happen at cathode, right? Because we are supplying the energy from the outside and it is a non-spontaneous process. The reduction reaction that took place at the cathode during discharge now will happen at the anode. Essentially, the electron flow is reversed compared to the discharge cycle. Okay, now we'll see a little bit of battery charging and recharging.
So first, how does your battery power your smartphone? Let's start from what we know. All batteries have a positive terminal and a negative terminal and supply power or electricity to our portable devices. So electricity is essentially a flow of electrons in our smartphone. Electrons which are negatively charged flow from the negative terminal and run things like the speakers or the display, and then end up in the positive terminal. So then, where does this flow of electrons come from? Well, this is a lithium-ion battery, so the electrons come from the element lithium. At the negative terminal, which is technically called the anode, lithium is stored between layers of carbon graphite, similar to the graphite in your pencil. Graphite has a nifty crystal structure of layered planes that allows the lithium to be wedged in between each of the layers. The technical term for this is intercalation. Graphite functions as a kind of like stable storage space for lithium atoms. Okay, moving on. One inherent property of the element lithium is that it doesn't like its outermost electron, and it wants to give it up. When there is an available path from the negative terminal to the positive terminal, this electron separates from the lithium and starts heading to the other side. At the same time, the lithium leaves the graphite and becomes positively, or +1 charged, and is now called a lithium ion. FYI, an ion is just a fancy word for an atom who has lost or gained an electron and thus is charged. When a lot of lithium atoms leave the graphite at the same time, a flow of electrons is built up. So, let's now jump to the positive terminal, which is technically called the cathode. Here we have cobalt, which has lost some electrons to oxygen, thus making the cobalt positive, or +4 charged. As a result, it wants to gain back an electron. So when we connect the negative and positive terminals to our smartphone, the electrons flow from the lithium, which wants to give up an electron, through the circuits and components in the smartphone, and to the cobalt, which wants to gain an electron. Now here we run into a small issue. With the flow of electrons from the negative to the positive terminal, the cobalt side grows more and more negatively charged, and the other side positively charged. Yes, the electrons do want to flow in this direction, but at the same time, electrons don't like to flow to an area that is growing more and more negatively charged. This is because opposite charges attract and similar charges repel. So to fix this, we give the now positively charged lithium ions that recently left the graphite a path to move to the other side. This path is called an electrolyte, and its function allows for the lithium ions to migrate over from one side to the other, while not allowing the electrons to move through it. When lithium gets to the cobalt side, it again wedges itself or intercalates with the cobalt and oxygen to become lithium cobalt oxide. The lithium isn't regaining its electron, that electron went to the cobalt. It's just balancing out the charge buildup. Let's quickly recap. Here is a full battery. Throughout the day, lithium atoms leave the graphite layers and separate from their electrons to become lithium ions. The electrons flow from the negative terminal through the circuits and components in the smartphone and into the positive terminal to join the cobalt atoms. At the same time, the lithium ions travel through the electrolyte in order to neutralize the charge buildup and keep the reaction going. Here's the chemical formula for the reaction. Thus, at the end of the day, almost all of the lithium has left the graphite layers, and joined the cobalt to become lithium cobalt oxide, and your battery is now running on empty. Now that the battery is empty, let's recharge it. We plug in our smartphone, and when we do this, the USB charger applies a higher force on a flow of electrons in the opposite direction. Electrons are pulled out of the cobalt, thus returning cobalt to its +4 state and kicking out the lithium ions. On the other side, electrons are forced onto the graphite, which pulls the lithium through the electrolyte and back into the layers of graphite. As you see, it's the exact opposite of the earlier reaction, which is why this battery is rechargeable. The lithium and its electrons move in one direction when you use the phone, and the opposite when you charge it back up.
I led the team that built Facebook Messenger. The world.
Let's rewind and add a few more details of note. First, these two sides can't touch. If the anode and cathode were to touch, and if there were any lithium left in the graphite, the chemical reaction would accelerate uncontrollably and cause a fire or often a small explosion. Thus, a non-conductive semi-permeable separator that allows the lithium ions to pass through is placed in the middle. And this electrolyte isn't an effective barrier because it's a liquid. The second thing to note is that the graphite and cobalt peroxide aren't good at collecting or distributing the electrons. Thus, a conductive copper layer is added next to the graphite, and a conductive aluminum layer next to the cobalt peroxide. These two layers, or sheets, are called collectors. Okay, on to third. These animations are showing 100% of the lithium moving from the anode to the cathode and back. But in reality, there will always be some percentage of lithium that remains in the anode, cathode, and electrolyte, despite the battery being fully charged or discharged respectively. Continuing to fourth, in order to maximize the capacity of the battery and allow the battery to fit in your smartphone, all these layers are folded and wrapped into a rectangular prism package. I know this is a lot, but fifth and final. In order to regulate the flow of electricity, additional circuitry is added to the top of the battery. This circuitry prevents overcharging and damage to the battery. So then the final topic. Why does your battery's max capacity reduce over time? There are several reasons, one of which is that sometimes lithium and the incoming electron react with the electrolyte and organic solvent to form compounds that are called solid electrolyte interphase, or SEI. SEIs irreversibly consume lithium and the electrolyte, thus reducing the overall quantity of lithium and thereby reducing the max capacity of your battery. Another reason is that when you fully discharge your battery until it's dead, it can result in too much lithium on the cobalt side, which causes the irreversible generation of lithium oxide and cobalt-2 oxide. These compounds are stuck in that state, which thereby reduces the amount of lithium and cobalt for future use. So one tip is to not let your battery run until it's empty. It's better to recharge your battery at 30 or 40% than to let it run until it's dead. That about wraps it up. When it comes to batteries, there are hundreds of different.
Okay, so that was the basic lithium ion battery, or how the batteries are there and why should we recharge it and why it's a non-spontaneous process. Next topic is the Voltaic pile, that is the first true battery. The Voltaic pile was the first electrochemical battery invented by Volta in 1800s. It demonstrated that electricity could be generated through chemical reactions rather than friction-based methods. The structure of the Voltaic pile is, the Voltaic pile consisted of repeating units of two different metal discs, electrolyte soaked separator, and stacking methods. That is, the metal disc and the electrolyte layers were stacked alternately, creating a pile or column. The topmost copper disc was the positive terminal and the bottommost zinc disc was the negative terminal. So some of the significance of the Voltaic pile is, first, practical source of continuous electricity, foundation of electrochemistry and electrical applications, inspired later battery designs, that is the lead acid battery. However, the voltaic pile had limitations such as leakage of electrolyte, short lifespan, and this. So we'll see what a voltaic pile is.
When I say power, you probably think of a power outlet. But the fact is, batteries were used long before electrical grids or generators were in use. The term battery was first used in 1749 by Benjamin Franklin to describe a set of capacitors he'd wired in series in order to produce a higher voltage. He was using the word in the sense of a set of units connected together in series. But it eventually caught on so well that nowadays we use the term battery to describe even a single power cell. Of course, Franklin's capacitors are not batteries in the modern sense. We define a battery as a container consisting of one or more cells in which chemical energy is converted into electricity and used as a source of power. It would be another 11 years before someone used a chemical reaction to reliably produce electricity. In 1800, Alessandro Volta stacked copper and zinc discs on top of one another, separated by pieces of cloth soaked in salt water. He called this a voltaic pile, and it was the first source of relatively reliable continuous electricity in convenient pile form. And this is considered the first definitive battery. The zinc discs served as anodes, the copper as cathodes, and the salt water was an electrolyte. With these simple materials, we can easily create our own voltaic pile.
Let's start by making a single voltaic cell in a beaker. The beaker cell produces 0.796 volts. Now I'll build a bunch of cells together as a voltaic pile, using these cardboard squares, which have already been soaked in the salt water. Not sturdy by any means, but this leaning tower of Volta produces enough power to light a 5mm blue LED. And for the record, that is 9 cells in the pile, producing 6.33 volts.
Not long after the voltaic pile was created, William Cruikshank came along and improved the design by laying it on its side in a slotted box. This helped prevent the electrolyte from leaking as the pile with his
was its use of a porous barrier copper cathode sitting inside of a porous earthenware pot filled with copper sulfate. This pot is then submerged inside of a container filled with zinc sulfate and encircled by the zinc anode. The porous earthenware allows ions to pass between the electrolytes, but hydrogen bubbles are prevented from forming. This greatly increased the cell's lifespan when compared to a voltaic pile.
The Daniell cell wasn't perfect, but its improved reliability made it suitable for widespread use. In fact, the standard for 1 volt is based on the output of 1 Daniell cell. All of the batteries we've talked about up until now would be considered primary, which means once their chemical reactions are depleted, that's it, they need to be replaced. Now, a secondary battery can be recharged multiple times and used again without being replaced, which is a good thing. In 1859, French physicist Gaston Plante created the first rechargeable battery using a lead anode and a lead dioxide cathode immersed in sulfuric acid. The chemical reactions inside Planck's lead-acid cell could be reversed by passing a reverse current through it. A pretty amazing feature, but its weight and size made it impractical for most uses. Still, it was suitable for some things. In fact, lead-acid cells are still used in cars today. So far, all of these early batteries have used liquid electrolytes, which pose pretty obvious challenges to portability. But in 1886, Carl Gassner created the first dry cell battery using an electrolyte paste composed of ammonium chloride and plaster of Paris. Because it didn't spill and could be used in any orientation, the zinc carbon cell opened the gates to many new portable uses, such as flashlights. The zinc carbon cell would eventually be refined by the National Carbon Company and evolve into our modern alkaline battery. You can easily see how little the design has changed over the years. Just a bit of help from a hacksaw.
It's densely packed, but all the elements are still here. A carbon cathode down the center, a thin shell of zinc serving as the anode, and a thick pasty black electrolyte.
Of course, more and more nowadays, when we think batteries, we think lithium. In fact, you probably carry around a lithium battery every day in your pocket. Because of its low density and high electrical potential, lithium has long been considered an ideal material for use in batteries. But it wasn't till the 1970s that the first primary lithium cells were made widely available. Further developments from researchers around the globe led to the release of the lithium-ion.
So you get the idea about how the batteries have been evolved and what exactly is a rechargeable battery and what was voltaic pipe. Now this was till now we have brushed over the chemistry part of the bioelectrochemistry. Here comes now the biological part of bioelectrochemistry. As you can see that this is a animal cell, this is a bacterial cell. At the end of the day, both of these are cells only. Okay. If we look at the difference in size of an animal cell and an average bacterial cell, it ranges from 1 micrometer, that is the bacterial cell, very small, and an animal cell excuse me, and an animal cell which ranges from 20 to 50 micrometer. Okay, so they are characteristically different cells. They have different components, yet they both are cells, right? So this is a typical example of prokaryotic cell, representation of prokaryotic cell, and this is a typical representation of an eukaryotic cell. So what is a prokaryote and what is a eukaryote? So as you can see, this blue thing, this is the nucleus, and no such organelle is found in the prokaryote cell, because prokaryotes does not have boundary defined nucleus. They have nucleoid, which is just an area in which their genetic material is spread in the cell itself. They are not confined to one particular space in the cell. So prokaryotic means prokaryon, karyon means nucleus, primitive nucleus, and eukaryotic means new nucleus. Okay, but despite all the differences between a prokaryotic cell and a eukaryotic cell, you can see that nucleus is not present in the prokaryotic cell, hence the nuclear membrane is not present in the prokaryotic cell. Membrane bound organelles such as mitochondria, Golgi body, these are not present in the prokaryotic cell. Okay, but there are some things which are common even between the prokaryotic cell and a eukaryotic cell. They are the plasma membrane, as you can see here, ribosomes, cytoplasm. Okay, so our concern is the plasma membrane, as it is present in both prokaryote and eukaryote, and they also have important function to perform, right? So just looking at the diagram, what is a major function which plasma membrane is performing? Even if you don't know anything about it, you don't know how it functions, what it is made up of, you don't know anything. But one thing is very clear when we just see a plasma membrane, is that it is the boundary of the cell. It is making the cell separate from its environment. It is giving the shape to the cell. Okay? Whenever we think of a cell, we first draw a circle or an oval, right? So what is that circle and an oval? It is a plasma membrane. Okay? Now, if we want to know more about plasma membrane or cell membrane, so what exactly it is? So the plasma membrane or the cell membrane provides protection for a cell. It also provides a fixed environment inside the cell, and that membrane has several different functions. One is to transport nutrients into the cell and also to transport toxic substances out of the cell. This is the basic representation of a cell membrane. The thing which you saw here, this boundary, if you zoom into it, it will something look like this. So what are the major components of plasma membrane or the cell membrane? First, you can see it is the phospholipid bilayer, which means this is one layer, this is another layer. It is made up of a type of lipid which is called phospholipid. Okay. Then what else we can see here? We can see some proteins, right? So we can see a protein channel, which is a transport protein. We can see a globular protein sitting here. We can see a peripheral protein sitting here. We can see a glycoprotein sitting here. We can see integral protein or the globular protein in this way. And then we can see surface proteins. We can see alpha helix proteins, and we can see some carbohydrates associated with the proteins, right? But one thing to notice is that these carbohydrates are not present towards the cytoplasm. They are present only towards the extracellular fluid. So these are some of the major components of a cell membrane. So what are the major components? First, that membrane is made up of lipid bilayer, and that lipid is of type phospholipid. Plasma membrane or cell membrane holds proteins also, but there are different types of protein. Some protein are crossing both the layers simultaneously, and they are called integral membrane protein. Some proteins are peripheral protein, as they are associated only towards the one side of the lipid. One protein is the one which is facing towards the outside of the membrane and is associated with carbohydrates called glycoproteins. And a protein which has alpha helix structure, they are called alpha helical protein, and they are transversing the whole plasma membrane. To look into more detail of how a plasma membrane looks like and what are its major functions, let us consider this and refer to this detailed video regarding plasma membrane. Okay.
Video, we will talk about cell membrane. The cell membrane is also called the plasma membrane or plasmalemma. It makes the outer protective wall of the cell. It maintains the shape and size of the cell. And obviously, any exchange between the inside and outside of the cell happens through the cell membrane only. Now let's talk about its structure. It's very thin and pliable. Its thickness is only about 10 nanometers. The main constituents of the cell membrane are lipids, proteins, and carbohydrates. Lipids make up about 40%, proteins about 55%, and carbohydrates about 5% of the membrane. Now let's talk about each of these components one by one. First, the lipids. The lipids are arranged in 2 layers, like a sandwich. Thus they make a lipid bilayer. It mainly has 2 types of lipids: phospholipids and cholesterol. Along with them, there are other types of lipids as well. Phospholipids are by far the most abundant among them. This is a phospholipid molecule. It has a phosphate head, which is hygrophilic. Means it likes to be with water. And a lipid tail, which is hydrophobic. This means it likes to stay away from water. So the phospholipid molecules arrange themselves in this type of bilayer form, where phosphate groups are on the surface in contact with water, and lipid groups are on the inside, away from water. This is called hydrophobic interaction. An interesting thing about this is that in this arrangement, the phospholipid molecules do not make any strong bonds with each other. These molecules are actually freely moving along the plane of the layer. Thus, the membrane is actually in a liquid state, not the solid one. This is called the fluid mosaic model of the membrane. Now, let's continue with the next lipid, cholesterol. Cholesterol molecules are dissolved in the lipid bilayer. It controls the fluidity of the membrane. At a modest concentration, it decreases the fluidity. Or in simple words, it makes the membrane more rigid. And at high concentrations, it increases the fluidity of the membrane. So these were the lipids. Talking about the permeability of the lipid bilayer, it's semi-permeable. As it's made up of lipids, other lipids and lipid-soluble substances can dissolve in it and thus pass through it. Water and water-soluble substances, as well as large molecules, cannot pass through it. The lipid bilayer makes the backbone of the membrane, to which the proteins and carbohydrates are attached. And that brings us to the protein component of the cell membrane. Proteins are mostly in the form of glycoproteins. Broadly, they are categorized into 2 types: integral membrane proteins and peripheral membrane proteins. Integral membrane proteins are tightly integrated with the lipid bilayer. And peripheral membrane proteins are loosely attached to lipids, or integral membrane proteins. The membrane proteins serve as transport proteins to allow passage of water and water-soluble substance, receptors to receive signals, as second messengers in intracellular signaling, as enzymes, as adhesion molecules to attach the cell to extracellular matrix or make cell-to-cell contact, form a submembrane cytoskeleton that provides strength and resilience to the membrane, and finally, they may be expressed as antigens. So these were proteins. Now let's see the last component of the cell membrane, carbohydrates. Most of the carbohydrates on the cell membrane are in combination with proteins and lipids in the form of glycoproteins and glycolipids. The carbohydrate portion in these molecules is usually dangling on the outer side of the cell. Along with these are also other carbohydrates attached loosely to the outer surface of the cell. All these carbohydrates cover almost the entire outer surface of the cell. This carbohydrate coating of the cell is called glycocalyx. Functions of the carbohydrates are as follows. Most carbohydrates have a negative charge. So they make the outer surface of the cell electronegative, which repels other negatively charged objects. Second, neighbor cells may get attached to one another through their glycocalyx. They may serve receptor functions. And finally, they may be involved in immune reactions. So this was all about the cell membrane. Now let's have a quick summary. The cell membrane makes the outer wall of the cell. The central lipid bilayer is made up mainly of phospholipids and cholesterol. It's fluidic in nature and permeable to only lipid and lipid-soluble substances. Attached to the lipid bilayer are proteins that serve as transport proteins, receptors, second messengers, enzymes, adhesion molecules, submembrane cytoskeleton, and antigen. And we also have carbohydrates, making the outer coat, called glycocalyx. The carbohydrates give the cell surface a negative charge, help one cell to attach to the other, serve as receptors, and participate in immune functions. That's it for this video. Click here to read.
Right? It was the basic functionality of cell membrane and the structures associated with the cell membrane. So what is a membrane potential? Why we are studying the membrane, right, in a bioelectrochemical subject? It's because at the end of the day we want the current to be passed. For current we need potential difference. Okay, so in the galvanic cell it was the difference due to the reduction potential of the material. But in biological system, from where are we getting this voltage difference or potential difference? Okay, so membrane potential, also transmembrane potential or membrane voltage, is the difference in electric potential between the interior and the exterior of a biological cell. It equals the interior potential minus the exterior potential. This is the energy, that is work per charge, which is required to move a very small positive charge at constant velocity across the cell membrane from the exterior to the interior. If the charge is allowed to change velocity, the change of kinetic energy and production of radiation must be also taken into account. Typical values of membrane potential, normally given in units of millivolts and denoted as MV, range from -80 millivolt to 40 millivolt to -40 millivolt. For such typical negative membrane potential, positive work is required to move a positive charge from the interior to the exterior. However, thermal kinetic energy allows ions to overcome the potential difference. For a selectively permeable membrane, this permits a net flow against the gradient. This is like osmosis. So we'll see what we are talking about with respect to the membrane potential.
Membrane potential, or membrane voltage, refers to the difference of electric charges across a cell membrane. Most cells have a negative transmembrane potential. Because membrane potential is defined relative to the exterior of the cell, the negative sign means the cell has more negative charges on the inside. There are two basic rules governing the movement of ions. They move from higher to lower concentration, just like any other molecules. Being charge-bearing particles, ions also move away from like charges and toward opposite charges. In the case of the cell membrane, there is a third factor that controls ion movement: the permeability of the membrane to different ions. Permeability is achieved by opening or closing passageways for specific ions, called ion channels. Permeability can change when the cell adopts a different physiological state. Consider this example. Two solutions of different concentrations of sodium chloride are separated by a membrane. If the membrane is equally permeable to both sodium and chloride, both ions will diffuse from higher to lower concentration, and the two solutions will eventually have the same concentration. Note that the electric charges remain the same on both sides and membrane potential is 0. Now let's assume that the membrane is permeable only to the positively charged sodium ions, letting them flow down the concentration gradient while blocking the negatively charged chloride ions from crossing to the other side. This would result in one solution becoming increasingly positive and the other increasingly negative. Since opposite charges attract and like charges repel, positive sodium ions are now under influence of two forces. Diffusion force drives them in one direction, while electrostatic force drives them in the opposite direction. The equilibrium is reached when these two forces completely counteract, at which point the net movement of sodium is zero. Note that there is now a difference of electric charge across the membrane. There is also a concentration gradient of sodium. The two gradients are driving sodium in opposite directions with the exact same force. The voltage established at this point is called the equilibrium potential for sodium. It's the voltage required to maintain this particular concentration gradient and can be calculated as a function thereof. A typical resting neuron maintains unequal distributions of different ions across the cell membrane. These gradients are used to calculate their equilibrium potentials. The positive and negative signs represent the direction of membrane potential. Because sodium gradient is directed into the cell, its equilibrium potential must be positive to drive sodium out. Potassium has the reverse concentration gradient, hence negative equilibrium potential. Chloride has the same inward concentration direction as sodium, but because it's a negative charge, it requires a negative environment inside the cell to push it out. The resting membrane potential of a neuron is about negative 70 millivolts. Notice that only chloride has the equilibrium potential near this value. This means chloride is in equilibrium in resting neurons, while sodium and potassium are not. This is because there is an active transport to keep sodium and potassium out of equilibrium. This is carried out by the sodium-potassium pump, which constantly brings potassium in and pumps sodium out of the cell. The resulting resting potential, while costly to maintain, is essential to generation of action potentials when the cell is stimulated.
Right? So this is the basis of potential in the biological system or across the biological membrane. So this is the similar thing which is represented in the figure form, that how small molecules are allowed across the membrane as the cell membrane or the biological membrane is selectively permeable. Okay, if you look at very small hydrophobic molecules, so with this the membrane is pretty permeable for these molecules and they transverse the membrane via diffusion itself. Okay, for small uncharged polar molecules such as water, urea, glycerol, so what happens is they are largely permeable, but some are not allowed across the membrane. So some can pass through osmosis or diffusion and some don't. And why not? Because they'll face a huge energy barrier when they are entering into the hydrophobic environment of the membrane, this part. Okay, large uncharged molecules or polar molecules such as glucose and sucrose, so membranes are largely impermeable for these compounds. They can only pass through facilitated diffusion or active transport. Then ions such as sodium, potassium, chloride, calcium, so membrane is completely impermeable to such ions and they can only pass through facilitated diffusion or active transport. So the thing which we have learned in the video itself, it is present here, and this is important to understand that from where the potential difference is present across the membrane, which is allowing for the electron to flow from one side to the other side. Okay, so if we look at the cell membrane right here, this is the lipid bilayer or the selective permeable lipid layer or the biological membrane. If you can see, outside is positive, inside is negative. So outside there is more concentration of sodium, outside there is more concentration of chloride, while inside we have more concentration of potassium. If we look at the concentrations on each side, so sodium is more outside, that is 150 millimolar, and inside it is 15 millimolar. Potassium is more inside, that is 150 millimolar, and outside it's only 6 millimolar. Chloride is more outside, that is 125 millimolar in comparison to 9 millimolar inside the cell. And calcium, it is more inside the cell, that is 10 nanomolar, and outside it is 1.2 millimolar. The types of transport. So we have seen that small molecules can transport via facilitated transport or active transport. So what do we mean by transportation across the membrane? So there are basically two modes of transportation across the membrane. And why we need these modes? Because membrane is selectively permeable. Okay, so the first mode is the passive transport, and the second mode is the active transport. The passive transport is simple diffusion and facilitated diffusion. Active transport is primary active transport and secondary active transport. So if you look in the diagram, simple diffusion is basically the molecules transporting or moving from their higher concentration to the lower concentration, that is along the concentration gradient. In facilitated diffusion, the molecules are transporting from their higher concentration to lower concentration, that is alongside the concentration gradient, but with the help of a protein. Okay, if we talk about active transport, in the primary active transport, the molecules are transporting from their low concentration towards higher concentration, that is against the concentration gradient, with the help of a protein, and energy is associated during this transportation. Secondary active transport, again the molecules are transported against their concentration gradient with the help of a protein, but in this directly ATP is not used, but the energy of one molecule which is transporting alongside the concentration gradient, that energy is used to transport another molecule which is being transported against the concentration gradient. Okay, so if we look at the transporters, as we have seen here, this is the different types of transportation. This is types of transporter. So first one is the channel, that is it transports from higher concentration to lower concentration. The rate is higher and it is gated, so it will have open and closed state. Then for transporters, there are three different type of transporters: uniporter, symporter and antiporter. In uniporter, one molecule is transported along their concentration gradient. In symporter, two molecules are transported, one along the concentration gradient and another against the concentration gradient. Third, in the same direction. In the antiporter, again one molecule is transported alongside the concentration, other is against the concentration gradient, and the direction of the transport is not same and it is opposite. Then we have ATP powered pumps, in which the transportation takes place from lower concentration to higher concentration, that is against the concentration gradient, and there is association of energy via ATP. Okay, and these are the rates through which they are transporting. Okay, if we talk about transportation, we have talked about cell membrane. At the end of the day, we need to connect all of it with the electricity, right? So where the electrons are coming into place? Here we need to understand an organelle which is called the powerhouse of the cell, and the name is mitochondria, and a function of this which is called electron transport chain. So mitochondria are double membraned organelles found in eukaryotic cells responsible for aerobic respiration and ATP production. Their inner membrane houses the electron transport chain, that is the final stage of cellular respiration. You don't need to worry about cellular respiration because it is not the scope of this subject. Some of the key features of mitochondria are outer membrane, it is permeable to ions and small molecules. Inner membrane, it is highly folded into cristae where the ETC takes place. Matrix contains enzymes for the Krebs cycle. Electron transport chain, so the ETC is the final step in aerobic respiration. Located in the inner mitochondrial membrane, it consists of 4 protein complexes 1 to 4 and ATP synthase. So the steps of the ETC include electron donation, electron transport and proton pumping, oxygen as the final electron acceptor, and last but not the least, ATP synthesis via chemiosmosis. So electron donation, NADH and FADH2. Electrons are transferred from NADH and FADH2 produced during the Krebs cycle to complex 1 and complex 2 respectively. Electrons transport or they move from complex 1 to 3 to 4, releasing energy to pump protons into the intermembrane space. At complex 4, electrons combine with oxygen and proton to form H2O. This is why oxygen is essential for the respiration. The proton gradient drives protons back into the mitochondrial matrix through ATP synthase, generating ATP from ADP. Okay, and this is the list of components of the ETS. So complex 1, 2, 3, 4 and ATP synthase. First complex is named as NADH dehydrogenase. Second complex is called succinate dehydrogenase. Third complex is called cytochrome B and C1. Complex 4 is called cytochrome C oxidase. And complex 5 is ATP synthase. Then each NADH contributes to 2.5 ATP while FADH2 contributes to 1.5 ATP. Overall, in an aerobic respiration, when we have eaten some food and that one molecule of glucose will ultimately lead to us, and it will provide us 38 ATP or 38 molecules of ATP or the energy. So the conclusion for the ETC is that few points which you should remember. The ETC in mitochondria is crucial for ATP production via oxidative phosphorylation. It creates a proton gradient that drives ATP synthesis, making it an efficient energy harvesting process. Disruptions in ETC, that is, there are certain toxic which disrupts the ETC. It can severely impact cellular energy production. Okay. These are some again basic topics which we have discussed during the previous week. So junction potential we discussed, electrochemical signals in metalloproteins we have discussed, nickel battery, the history of it, alkali metals, why we use alkali metals in the batteries and all. So all these are very basic things which we have already discussed, and I hope that if your exam is in the coming week or in the coming month, I wish you all the best for that, and feel free to reach out to me. You can ask me any questions, any doubts. I'll be happy to help you out. Okay, so thank you for your patience and thank you for attending this course. I hope you have learned something, and all the best. Thank you.